In this segment, I want to talk about projectile motion. What do I mean by projectile motion? Projectile motion is what happens when you toss a ball through the air. So that was projectile motion. That ball flying through the air was projectile motion. That's what I'm talking about, right? That was projectile motion. Anytime we got a ball flying through the air under the influence of gravity alone, we're talking about projectile motion. So in the previous chapter, we talked about free fall. And we talked about how a ball moving up and down is in free fall the entire time. And so we solved problems with the ball moving straight up and straight down. Recall that we said that was free fall because the ball is under the influence of gravity alone. Because it's under the influence of only gravity, we call it free fall. And gravity always pulls down, which means that the acceleration is in the downward direction. And hopefully I've convinced you all by this time that the acceleration is always in the downward direction and always 9.8 meters per second squared. And if we're calling down negative, then it is negative 9.8 meters per second squared. So it's negative 9. The acceleration is negative 9.8 meters squared when the ball is going up, when it stops briefly at the top, and when it is going back down. Always negative 9.8 meters per second squared. Now, what if instead I toss the ball like this? Okay, so now I've given it some horizontal velocity as well as the up and down motion. Okay, how is that different? Well, in a way it's not really that different at all, because we still have gravity. Gravity still pulls straight down. And so gravity is only affecting the vertical component of that motion. It's not affecting the horizontal component of that motion. My dad likes to shoot guns for fun. And I remember when I was a kid going out with my dad one time, and he said to me, if you drop this bullet at the exact same time as you shoot the gun, those two bullets will hit the ground at the exact same time. I didn't believe him, but now I do. And of course, in order for this to be true, we have to neglect air resistance and assume we're shooting the bullet over level ground. But it's true. If a bullet has a very large velocity in this direction, and gravity is pulling down on it, then this velocity in this direction, it doesn't affect how long it takes to hit the ground. What affects how long it takes to hit the ground is its vertical motion. And its vertical motion is affected by gravity, but its vertical motion is not affected by the horizontal velocity. So here we have a little schematic here, and this is kind of what I'm getting at. This red ball has been dropped, and this yellow ball has been shot horizontally. And then we've got this stop motion picture frame that shows that each of the vertical displacements at every interval is exactly the same, right? So whether it's the yellow ball that has some horizontal velocity or the red ball that's just dropped straight down, either way, the vertical motion is identical for those two balls. And I'll show you just a little video that captures this in real time. All right, so first we're going to see this yellow ball drop straight down, and now we're going to see the red ball shot, and now we're going to see it both at once. And we see, indeed, they do hit the ground at the same time. Here it is in slow-mo. Both balls are in free fall because both balls are under the influence of only gravity. Okay, so again, we just saw the version of this in real time, and so hopefully I've convinced you now that this is a true thing, right? That the motion of that's horizontal motion just doesn't affect the vertical motion. They're independent, and so that's one of the. We're going to use this idea all through this semester, that motions that are perpendicular to each other are really independent of each other. And so here's a quick motion diagram of maybe a tossed ball, right? So maybe this is a motion diagram of that motion right there. And what do we see here is this has been given some velocity. And so it's been launched here, and we could draw the initial velocity like this. Right? And of course, if we're using a standard x and y coordinate system, then we can break this velocity into its components. If this is v initial, then this would be our v sub x, and this would be my v sub y initial. In this particular case, shown in the PowerPoint, I've given these numbers, and these numbers are 19.6 meters per second in the vertical direction and 10 meters per second in the horizontal direction, so that we can see how these things change. And my motion diagram shows positions of this ball in 1 second intervals. So obviously this is a ball that is thrown much higher than that. Oh, I don't have room to do that in my basement. You'll have to trust me. Okay, so this is a ball that's been thrown much higher than I can do in my basement. And it's given an initial velocity such that the horizontal component is 10 meters per second and the vertical component is 19.6 meters per second. Well, what do we have? For this ball flying through the air, we have what forces are acting on it. Well, we haven't quite talked about forces, but remember that a force is a push or a pull in a certain direction. We have gravity pulling down. We haven't and we're neglecting air resistance, so it's just gravity pulling down. It's in free fall. The only force acting on it is gravity. So as it's flying through the air, we've got this force pulling it down. We're neglecting air resistance, so there's nothing pushing horizontally. So what happens to its speed in the horizontal direction? It doesn't change. Its velocity, I should say, in its horizontal direction. It doesn't change. It's 10 when it leaves my hand. It's 10 after 1 second. After 2 seconds, still 10. 3 seconds, and right before it hits the ground, it's still 10 meters per second. Now, we have to clarify something here. We use this language a lot in physics, of right when it hits the ground. What's its speed when it hits the ground? And well, if I throw that ball, then yes, once it hits the ground, it's going to stop. But I'm never going to be asking for you to tell me that in a physics problem. Why? Because once it starts hitting the ground, there's all kinds of forces involved. It's no longer in free fall. Its acceleration is no longer constant. We've got force from the floor, there's friction, there's all kinds of weird things happening. So when I say something like, what's its velocity when it hits the ground, I'm talking about this magic moment when the very first fuzzies of the edge of the ball have started to hit the ground, but it doesn't slow down yet. So it's got no farther to fall, but it hasn't slowed down yet. I mean, that instant of time, it doesn't even last that long. But it does exist. That's what I'm talking about. Okay, so going back here, we see that right before it hits the ground, or as it's hitting the ground, its velocity is 10 meters per second in the horizontal direction. It hasn't changed because there's no action, no forces pushing or pulling in the horizontal direction. Let's look at the vertical direction. In the vertical direction, we simply have free fall motion, and we know that any object in free fall has an acceleration of negative 9.8 meters per second squared in the y direction, downward at 9.8 meters per second squared. And that means that every second, the velocity in the y direction will change by negative 9.8 meters per second. And so if we start at 19.6 meters per second in the vertical direction, then 1 second later, guess what? We are at 9.8 meters per second. Why? Well, we can just make a quick chart here. At 0 seconds, my velocity in the y direction was 19.6 meters per second. And this will be seconds. After 1 second, it is 9.8 meters per second. Now, why is it 9.8? Because every second, the velocity in the y direction changes by negative 9.8 meters per second. And so notice here that I've taken away 9.8 meters per second. What is its velocity in the y direction after 2 seconds? Well, it's 0. Again, I've taken away 9.8 meters per second. Remember, that's what meters per second squared means. It means meters per second per second. Every second, I have to subtract 9.8 meters per second from the velocity. So what is it after 3 seconds? Well, it must be negative 9.8 meters per second. And after 4 seconds, it is negative 19.6 meters per second, and it has hit the ground. And each one of these, notice, changes by negative 9.8 meters per second. So again, we've got free fall motion in the vertical direction and constant motion in the horizontal direction. That's projectile motion. That's really all there is to it. And we've already learned how to solve one-dimensional problems. So in a way, projectile motion is not one hard two-dimensional problem. Really, it's two not so bad one-dimensional problems. And I'll show you exactly how that works here in just a minute. So the big picture here is that the horizontal and vertical components are independent from each other. We have uniform motion at constant velocity in the horizontal and free fall motion in the vertical, as I just said. One other thing, and we can see that here, if the launch height and the impact height are the same, then the parabolic path of the projectile is symmetrical. And you can see that this is a nice symmetrical parabola. Notice that the velocity vector here just mirrors the velocity vector here, right? And so it takes the same amount of time up, takes the same amount of time down. It'll hit the ground at the same velocity, the same speed as it left my hand at. Again, only if the launch height and the impact height are equal. So here's just a little chart, and it basically just shows, kind of comparing the vertical motion and the horizontal motion here. And so in the horizontal direction, we have constant velocity. Our acceleration is 0. And we have that Vx is Vi cosine theta. And I've erased my picture that I had going over here. But we could just see that from that triangle. So this is Vx. It's not Vx initial. Why not? Well, because the Vx doesn't change. Remember, the acceleration is 0 in the x direction, so we don't need an initial and a final velocity in the x direction. There's only one velocity in the x direction. Notice that Vx is adjacent, and so we could write that the cosine of theta equals adjacent over hypotenuse, or right. And so again, I'm just solving that triangle. Similarly, Vy initial is V initial times the sine of theta. And so notice that, and we call this angle here theta, we call this the launch angle. In the x direction, we have acceleration equal to 0, and in the y direction, we have the acceleration is negative g, or negative 9.8 meters per second squared. Okay, our basic steps then. We're going to use the particle model, and recall that the particle model is where whether we're tossing a ball, a Buick, a piano, a clown, then we assume that all of that mass is centered at a dot. We call that the center of gravity, or the center of mass, and we'll save defining that term for a bit later. But we imagine that all of the mass is concentrated at a single point, okay? And then moving on, our steps here, we're going to draw a picture with initial and final points. It's very important. It's very important to take the time to draw your picture, and it's important to take the time to label your initial and your final points. Much like with one-dimensional problems, there's no right or wrong answer to which should be my initial and what should be my final. It's really just up to you, as there are better choices and worse choices sometimes, easier choices, hard choices. But remember, initial and final does not mean the beginning of everything and the end of everything. We're going to define a coordinate system. I'm going to emphasize this as a step from here on out because we may need to occasionally tilt our coordinate system, but not with projectile motion. For projectile motion, we're always just going to use a standard coordinate system. Again, our goal is to keep the acceleration in one dimension. I've just been talking for like 15 minutes about how the acceleration is only in the vertical direction, and so a standard coordinate system works fantastically here. And then we basically make our list of our 5 variables. But now we have a vertical problem and a horizontal problem. And so now we need a list in the x and in the y. In the x direction, things are pretty simple, right? Because the acceleration is always 0. And so the initial velocity and the final velocity are therefore the same. So really we only have 3 things in the x direction, and in the y direction we still have our 5 things. Now we do know that the acceleration in the y direction will always be negative 9.8 meters per second squared. These lists are independent with one exception, delta t, right? There really is only one ball, right? Our problem-solving strategy is to separate out the x and the y. We can solve them as separate problems almost. But really, we know there's only one ball, one Buick flying through the air, and therefore, there's only one time of flight. So delta t is the same for both. Okay, so our general problem-solving strategy often is we're going to use one direction, x or y, to obtain delta t, and then move to the other side to answer the question. Now, that doesn't work every single time, but it's often a good strategy. And the thing that works every time is we just figure out what we can in one dimension, and then use that to help us figure out what else we need in the other dimension. But we can really treat them separately, and the other thing that's always works is delta t is really the link that connects the x to the y. Well, I think we should just dive in and try an example. Okay, here's an example. I slide a coin off a 1 meter high table with a horizontal top. The coin is moving 5 meters per second as it leaves the table, and we're going to answer these questions. How far away does it land? What is its impact angle? And at what speed does it hit the ground? Okay, so that's a lot of questions. We're just going to take it one at a time. And really, this list of questions here, I mean, we don't really do a different strategy if we have different questions here. Either way, we're going to follow this list of steps. We're going to use the particle model. We're going to treat the coin as just a little dot. Now we need to draw a picture with initial and final points. We can do that. Okay, here we go. Here's my tabletop. And I'm going to slide a coin off of it. And it's going to do that. Okay? One of the first questions is how far does it land? So there's my delta x. It tells me that it is a 1 meter high tabletop. So that means that this distance here is 1 meter. And it tells me that initially it is going 5 meters per second. Okay, so that's its initial velocity. This is a lovely drawing. I need to label my initial points and final points. Now, in this case, I don't think this is too tricky. I'm going to just let my initial point be right here, right as it is leaving the edge of the table, and my final point will be right here, that split second that I was just talking about, right before it hits the ground, as it's hitting the ground. That's the final point. Okay, so there we go. There is my initial and final points and my nice drawing. What's my next step? I should define a coordinate system. Well, shoot. We're going to use a standard coordinate system, as I've said. We want to get in the habit of taking the time to define a coordinate system because a standard coordinate system is not always the best choice, as we'll see here in a little bit. Okay, my next step is to do my list of variables. In the x direction, I have delta x, delta t, and v sub x. In the y direction, I have delta y, delta t, v initial y, v final y. Let's see what I can fill out. And I really recommend that you just write out this whole list. It's definitely the best way to organize your thoughts. Okay. Delta x, that's what we're looking for. Delta t, man, we don't know that either. V sub x, do we know that? Oh, we do. That's what we gave here, right? So this is 5 meters per second. How do we know that's not in the y direction? Well, because the problem states that it is a horizontal tabletop. So if the coin is moving horizontally, then it's only got a velocity in the x direction. Moving on. Notice we've only got one of these, right? And, of course, we cannot solve for the other two if we only have one, right? So moving over here, we've got delta y. Do we know that? We do. It's 1 meter, but be careful. Since the coin is moving down, it is negative 1 meter. We've defined up as positive. Therefore, if the coin is moving down, its displacement is negative 1 meter. Delta t, definitely don't know that. Ooh, this is a tricky one. V initial in the y direction. That's 0. Again, because it's a horizontal tabletop. As it leaves the table, it is not moving in the y direction. VF, V final in the y direction. Some of you might be tempted to say 0, but again, I'm not talking about once it hits the ground. I'm talking about that magic moment right before it hits the ground. So we don't know that. Oh, and I missed A on my list here. I apologize. We need A. We need 5 things in Y. We need 3 things in X. In A, we need negative 9.8 meters per second squared. Great. There is my list of 5 things. Remember this rule that I've told you, right? If we know 3 out of the 5, we can always find the other 2. I know 3 out of the 5, I can always find the other 2. You know what? At this point, I'm not asking about v final in the y direction. I'm going to need that here in a bit. At this point, I really need to get... I'm asked for how far away. And, I guess, as a beginning student, you might look at this and you might say, hey, equation number 2 in the x direction, and I'm going to write it over here and then we'll move it, actually. So remember that equation number 2 looks like this. So there's my equation number 2. And notice then, if the acceleration is 0 in the x direction as it is, then this whole term goes away, right? And so we end up with this fairly straightforward version of my delta x, right? So we have delta x equals v initial times delta t. Well, if you look at this, we're asking for delta x. We know Vx, and again, we don't need initial and final because it's not changing. So if we could figure out delta t, then we'd be able to answer this question. Now, we don't have enough information in x to figure out delta t, but looking at y, remember, if you have 3 out of the 5, you can always find the other 2. So we can definitely find delta t, can't we? And in fact, I think that we could use equation number 2 to do that, but we'll apply it to the y direction. So in the y direction, then, we would have delta y equals v initial delta t plus 1/2 a delta t squared. Okay, so let's look at this. We've got the v initial in the y direction. What is that? That's 0. This whole term goes away, doesn't it? And so now I can just do a little bit of algebra. Isolating delta t, we get that delta t equals the square root of 2 delta y over a. Well, we know all that information, so we can just plug in our numbers and run our calculator. And when we do that, we get 0.45 seconds. Is that a reasonable answer? Let's see. Sure, seems reasonable. Okay, something less than a second. So now I've got my delta t. I can haul that back over to the x. There's only one coin, even though intellectually we're separating out the x and the y. There's only one coin, only one delta t. I take it over here and I say delta x equals my velocity in the x direction, 5 meters per second, times 0.45 seconds gives me a delta x of 2.25 meters. Is that a reasonable number? Well, I think so. It's about 6 feet. 5 meters per second is about 10 miles an hour. Seems reasonable. I like it. What's next? Next it says, what is its impact angle? And at what speed does it hit the ground? Okay, so what we really need to do now then is we need to zoom in on its final velocity, right? If we think about what this coin is doing right as it's hitting the ground, it's got some velocity vector that looks like this. And we need to find the components of that velocity vector in order to find the speed and the angle. I'm going to make some room on my chalkboard. Okay, so now I've made a little room on my chalkboard, and I have filled in the pieces that I've now found. Those are in orange here. See? So the pieces here in orange are parts that I've found since we started doing the problem. And now I've drawn my final velocity vector right here, right? So this penny, it's going to fly off the table. It's going to go like this. It's going to hit the ground. Yeah, it's going to be doing something like this as it hits the ground. Again, we're talking about that moment right before it hits the ground. So here's my final velocity triangle. Now v sub x, we know that. That doesn't change. The acceleration is 0 in the x direction. This is 5 meters per second. How about Vy? Well, we need to find that. But if you look at this, we now know 4 out of the 5 here. So we can find Vy final in a fairly straightforward way. We just need to use equation number 1. Let's write that down. If we apply this to the y direction, well, we know v initial in the y direction is 0, so that goes away, which tells us that v final in the y direction equals a negative 9.8 meters per second squared times delta t, 0.45 seconds. And now we can just run our calculator, and we get 4.41 meters per second. And so now we can add that over here. Vy final is 4.41 meters per second. Okay, so now we've got the 2 legs of our triangle. We can always find the third leg, and we could use a tangent to find the angle. So that's how we can answer this question. What is its impact angle is the next thing it says. And so we know the opposite, we know the adjacent, so we can do inverse tangent to find the angle. So theta equals tangent inverse of opposite, 4.41, over adjacent, 5. And when you run your calculator, I got 41.4 degrees. There's my impact angle. And what is my final speed? The speed right before it hits the ground. For that, I need to find the hypotenuse of this. And so we have v final, we'll use the Pythagorean theorem. That's the square root of 5 meters per second squared plus 4.41 meters per second quantity squared. And we run our calculator. We get 6.67. Okay, so there we go. We've answered all of the questions. We've answered how far it went, how far from the table leg did it land. We've answered what is its impact angle, and what is its, at what speed does it hit the ground. Let's take a step back and recognize what we've done here, right? We've really treated this as x problems and y problems, right? Nowhere did I ever have an equation where I combined some bit of information from x and some bit of information from y, right? I never did that, right? We're solving x problems, we're solving y problems. The connector here is the time. There's only one time because there is only one penny. And I guess the other thing is, make your list, right? If you've got 2 out of the 3 here, you can always find the third. And if you've got 3 out of 5 here, you can always find the other 2. And so maybe, you can't directly answer the question. Maybe you can't answer the question right away that's been asked. Well, you start chipping away at this list, right? The way that here, I was asked for delta x, but that's not the first thing that I found, right? The first thing that I found was delta t. So you just start chipping away at this list. Eventually, you'll be able to fill in all the gaps. All right.